Welcome to this presentation. In this section, we are going to examine a practical problem in the field of operations research and resource allocation optimization. The problem statement is as follows. We need to transport exactly 513 passengers. Our objective in this model is to fully satisfy this demand using the available fleet in such a way that our objective function, which is the total operational flight cost, is minimized. To solve this integer allocation problem, we will utilize the dynamic programming technique. On this slide, you can see the technical and economic specifications of the three available aircraft types. The cost structure for each aircraft includes a fixed or initial setup cost and a variable cost per unit. Obviously, if a particular aircraft type is not used, its cost will be zero. As shown in the table, the Type 1 aircraft with a capacity of 200 passengers has a cost function of 10 plus 3x. The Type 2 aircraft has a capacity of 170 and a cost function of 8 plus 3x. Finally, the Type 3 aircraft, with a capacity of 80 passengers, has the most economical fixed cost, and its cost function is defined as 5 plus 2x. These parameters will form the basis of our recursive function calculations in the dynamic programming stages. To address this optimization problem, we employ the backward induction technique within the framework of dynamic programming. In this model, the parameter En represents our decision stages, where each stage corresponds to a specific aircraft class. The state variable I indicates the volume of remaining passenger demand at any given point, while the decision variable, K, specifies the number of aircraft allocated during that stage. Another critical component here is the state transition function, which characterizes the system's dynamics. This function dictates how, upon making an allocation decision in the current stage, the fulfilled capacity is deducted from the current demand, thereby calculating and updating the state, that is, the remaining demand for the subsequent stage. The fundamental structure of our model is governed by the Bellman recursive equation, as shown at the bottom of the slide. This equation ensures that the optimal cost at each stage is determined by minimizing the sum of the immediate cost of the current decision and the optimal cost of the remaining stages associated with that state transition. We begin solving the problem using a backward induction approach, starting with stage 1, which involves allocating the Type 3 fleet with a capacity of 80 passengers. However, before calculating the costs, we must determine what demand values, or state variables I1, might be carried over to this stage. To find the possible state space, look at the left table. The state values in this table are derived from the equation I1 equals 513 minus 170 K2 minus 200 K3. In fact, we consider all possible combinations of allocating Type 2 aircraft with a capacity of 170 and Type 1 aircraft with a capacity of 200 in the subsequent stages to see how many passengers remain for the current stage under each scenario. For instance, if only one 200-passenger aircraft is allocated in the other stages, substituting these numbers into the equation yields a remaining demand of 313 passengers entering this stage. Since this stage is the final step in covering the demand, all remaining individuals must be transported by the 80-passenger aircraft. Therefore, the optimal decision variable, K sub 1 star, is obtained by dividing the number of remaining passengers by the capacity of 80 and rounding up to the nearest integer. Now, let us turn to the right table and examine the optimal cost calculations based on the cost function. Cost 1 of key equals 5 plus 2k for each individual state. Row 1, I1 equals 0. If no passengers remain, it is obvious that we need 0 aircraft incurring no cost. Row 2, I1 equals 3. For 333 passengers, dividing 3 by 80 equals 0.03, which rounded up means we need 1 aircraft. Substituting this into the function, the cost is 7. Row 3, I1 equals 113. For 113 passengers, the division yields 1.41. Thus, we need a minimum of 2 aircraft. The calculated cost is 9. Row 4, I1 equals 143. For 143 passengers, the result is 1.78, requiring 2 aircraft once again. The optimal cost in this case will also be 9. Row 5, I1 equals 173. With 173 passengers, the division results in 2.16. Therefore, by allocating 3 aircraft, an optimal cost of 11 units is obtained. Row 6, I1 equals 313. For 313 passengers, the result is 3.91, which rounds up to 4 aircraft. The allocation cost in this scenario is 13 units. Row 7, I1 equals 343. For 343 passengers, the division yields 4.28, which requires 555 aircraft. The corresponding cost is calculated at 15 units. Row 8, I1 equals 513. Finally, if no other aircraft have been allocated in the preceding stages and all 513 passengers reach this stage, the division will yield 6.41. Therefore, we require 7 aircraft of this fleet type, which will result in the maximum cost for this stage, namely 19 units. This table serves as our computational foundation, providing the optimal values of the Stage 1 cost function to be used in the Bellman equations for the subsequent stages. We now reach the second stage, allocating the Type 2 fleet with a capacity of 170 passengers. Our approach in this stage utilizes the Bellman recursive equation. This equation helps us find the best decision, the optimal number of Type 2 aircraft, for any number of incoming passengers to this stage. First, let's look at the table on the left. This table calculates the possible values for the input state I2. These values are derived from the equation I2 equals 513 minus 200 K3, where K3 is the number of Type 1 aircraft with a capacity of 200 that might be allocated in the next stage. For example, if one Type 1 aircraft is allocated in the next stage, 313 passengers will enter this stage. Now let's move to the main calculations in the right table and examine it row by row. In each cell, we add the current cost of allocating Type 2 aircraft to the optimal cost from the previous stage. In row 1, I2 equals 0. If no passengers enter this stage, obviously no aircraft are needed and the cost is 0. In row 2, I2 equals 113. If we select 0 Type 2 aircraft, the current cost is 0, but all 113 passengers transfer to the previous stage. From the previous stages table, we know the optimal cost for 113 people is 9 units, thus the total cost is 9. If we select 1 Type 2 aircraft, the current cost is 11. Since the 170 passenger capacity of this aircraft fully covers the 113-person demand, we have no remaining passengers for the next stage. Therefore, the total cost remains 11. Result: comparing these two options, the minimum between 9 and 11 is 9, which yields the optimal decision of selecting 0 Type 2 aircraft. In row 3, I2 equals 313. If we select 0 Type 2 aircraft, the current cost is 0, and the optimal cost for 313 passengers from the previous stage is 13, making the total cost 13. If we select 1 Type 2 aircraft, the current cost is 11. The number of remaining passengers is 313 minus 170 equals 143. The optimal cost for this number from the previous table is 9, making the total cost 20. If we select 2 Type 2 aircraft, the current cost is 14. The capacity of 2 aircraft is 340, which exceeds the total demand of 313. Thus, the demand is fully covered, we have no remaining passengers, the cost for the next stage is 0, and the total cost is 14. Result: the minimum among 13, 20, and 14 is 13. So, the optimal decision here is to select 0 Type 2 aircraft. In row 4, I2 equals 513. If we select 0 Type 2 aircraft, the current cost is 0, and the optimal cost for 513 passengers from the previous stage is 19, making the total cost 19. If we select 1 Type 2 aircraft, the current cost is 11. The remaining passengers are 513 minus 170 equals 343. The optimal cost for this number from the previous table is 15, resulting in a total cost of 26. If we select two Type 2 aircraft, the current cost is 14. The remaining passengers are 513 minus 340 equals 173. The optimal cost for this number from the previous table is 11, resulting in a total cost of 25. If we select three Type 2 aircraft, the current cost is 17. The remaining passengers are 513 minus 510 equals 3. The optimal cost for this number from the previous table is 7, resulting in a total cost of 24. If we select four Type 2 aircraft, the current cost is 20. The capacity of these four aircraft is 680, which covers all 513 passengers. Thus, the demand is fully covered, there are no remaining passengers, the cost for the next stage is 0, and the total cost is 20. Result: among the numbers 19, 26, 25, 24, 20, the minimum cost is 19, yielding the optimal decision of selecting 0 Type 2 aircraft. This table summarizes the optimal results for the second stage, which we will use in the final stage's calculations. We reach the third and final stage of solving this problem, which is the allocation of the Type 1 fleet with a capacity of 200 passengers. Since we are solving the dynamic programming (DP) method backwards, this stage is actually the true starting point of our problem. For this reason, here I3 equals 513, meaning that at the very beginning, all 513 passengers are waiting for aircraft allocation, and we must make a decision for all of them. The table below shows the calculations for this stage based on the cost function of this aircraft type. Let's examine this table cell by cell. In the case of allocating 0 Type 1 aircraft, the current cost is 0. All 513 passengers are transferred to the previous stage, the upper table. According to the summary table of the second stage, the optimal cost for 513 passengers is 19. Therefore, the total cost equals 19. In the case of allocating one Type 1 aircraft, the current cost according to the formula is 13. Given the 200 passenger capacity of this aircraft, 513 minus 200 equals 313 passengers remain for the next stage. Looking at the upper table, the optimal cost for 313 passengers is 13. As a result, the total cost will be 26. In the case of allocating two Type 1 aircraft, the current cost according to the formula is 16. The capacity of two aircraft is 400 people, so 113 passengers remain. From the upper table, we see that the optimal cost for 113 passengers is 9, therefore the total cost becomes 25. In the case of allocating three Type 1 aircraft, the current cost according to the formula is 19. The capacity of three aircraft is 600 people, which covers all 513 passengers. Here, no passengers remain, so its cost in the previous stage is 0. Thus, the total cost will be 19. By comparing the calculated total costs, the minimum cost is 19. However, the very important point is that this minimum cost has occurred in two different scenarios. This means we have two distinct paths or policies that are equally optimal and yield the lowest possible cost for the airline. Let's trace back these two paths. In the first path, if we allocate no Type 1 aircraft, all 513 passengers proceed to the previous stage. According to the last row of the upper table, for 513 passengers, the optimal number of Type 2 aircraft is 0, and the optimal number of Type 3 aircraft is 7. Therefore, the first optimal fleet configuration consists of 7 Type 3 aircraft and 0 aircraft of the other two types. In the second path, if we allocate 3 Type 1 aircraft, all passengers are covered. The input to the previous stage becomes 0. According to the first row of the upper table, for an input of 0, we do not need any Type 2 or Type 3 aircraft. Therefore, the second optimal fleet configuration consists of 3 Type 1 aircraft and 0 aircraft of the other two types. We have reached the end of this fascinating fleet optimization problem. As you saw, using the dynamic programming approach not only helped us find the absolute minimum cost of 19, but it also revealed two entirely different optimal policies to achieve this goal. This is the true power of dynamic programming, providing decision makers with the flexibility needed for real-world scenarios. Thank you for staying with me until the end of this video. If you have any questions about the formulations or the step-by-step solution, please leave them in the comments section below so we can discuss them. For more videos on operations research and mathematical modeling, please subscribe to the channel. Until the next video, goodbye.